Welcome to the final chapter of our first unit, which is chapter 3, Matter and Energy. And this is the first lecture out of that chapter, which will cover sections 1 and 2 in your book. Section 1 is classification of matter. And matter is anything that has mass and takes up space, which sounds all-inclusive. You might think that, well, everything in the universe obviously is matter because everything that exists has mass and takes up space, but you would be wrong. Examples of things that do exist that are not matter would be light, or heat, or your thoughts, memories stored on computer chips. These are things that exist. You can access, songs on your phone. But is the song physically there with a certain mass? No, it's stored as a magnetic code in a sense. So let me write these down. Light, heat, energy, ideas, your thoughts, whatever. Those are forms of not matter. Now, the reason light can be considered not part of matter is that although it is made up of photons, those photons have no mass. All right, so pure substances are types of matter that have a fixed or definite composition. And pure substances can be either an element or a compound. Those are the two types of pure substances. So the properties in pure substances are identical and definite throughout the entire sample of that substance or matter through all proportions, and it doesn't matter the source of it. So for example, water is always water. It doesn't matter if you get the water from an asteroid out in space. It doesn't matter if you get it from our atmosphere. It doesn't matter if you get it from the ocean or from your tap at home, from your toilet at home, whatever. It's still H2O always. Now, honestly, water is almost always impure, but if you were to take the water and purify it through distillation or filtration or something like that, it would be pure water, pure H2O, and it wouldn't have any different properties no matter what source of that water you got it from. Elements are the simplest type of matter, or pure substances. They cannot be broken down into simpler substances by chemical means, and they're composed of the atoms. You can find the elements by looking at a periodic table anywhere online, in your textbook. Who knows? It's on Blackboard as well under the course documents. Those are the elements. There's 118 of them that are known. There may be more, but there's no less than 118. You can break apart an atom of an element into protons, neutrons, and electrons, but those and the quarks that make them up can't actually exist individually by themselves and give properties of matter. So the element, and the atom of the element, although not the smallest form of matter, compounds are substances that have two or more different elements in them. So they're not the simplest type of substances or matter. They can be broken down through chemical means into simpler substances. They can be broken down into simpler compounds, or they can be broken down into elements. For example, if I take water and I add electricity to it, I can break it down into hydrogen gas and oxygen gas. I need to balance that, so I would put 2 in front and 2 in front right there. Now, both of those are elements. But I can take a different compound, peroxide, and break it down, and it will give me a compound and an element. So for example, hydrogen peroxide is H2O2. If I just let it sit in the presence of light, another form of energy like electricity, it will give you water and oxygen. And it's not balanced here, so there we go, and there we go. It is now balanced. So that's why they're stored in brown bottles, the hydrogen peroxide, because it decomposes in the presence of light into a compound and an element. H2O is simpler than H2O2, so that's a decomposition. This picture here just shows how we could classify pure substances. We've got elements on the left, compounds on the right. Elements, there's two types of, I didn't mention it in the previous slide, but there's atomic elements and then there's molecular elements. We'll go through those more later on, but I'll write them in here now. The ones that are molecular are going to be hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. All of those are diatomic homonuclear elements. Homonuclear meaning they have the same nucleus, but there's two others that are not diatomic. There's sulfur and fluorine. Sulfur is S6 and phosphorus is P4. Now, on the compound side, we have molecular compounds and we have ionic compounds. And we will definitely get to those later on. The bonding nature of those compounds are different. Molecular compounds share electrons, ionic compounds have a transfer of electrons. But we'll get to that again later on when we learn about bonding. Alright, so we have pure substances and we have mixtures. All matter can be described as either of those two types of matter. And so mixtures are types of matter with more than one pure substance, and they have to be physically combined, not chemically combined. A homogeneous mixture is a mixture in which the composition is uniform throughout, and that means that the individual components of the mixture cannot be distinguished. Picture in your head some Kool-Aid. Kool-Aid, if it's red, for example, has water, sugar, dye. There's probably a bit of salt. There's probably some preservatives in there. I don't know. I'm not looking at a thing of it, but there's many different things in those mixtures that you make. And when you mix it all together, you cannot see those different parts. It looks like a red liquid. It's not a red liquid, it's a red mixture, in a sense. Water is the main component of it, and that's what would be called the solvent, which is the most prevalent component of a homogeneous mixture. Everything else in there, the salt, the sugar, the dye, preservatives, those are going to be called solutes. And I have here the word solution. That's just another name for a homogeneous mixture. That's the way it's most commonly called. Now, if we have homogeneous mixtures, we have to have heterogeneous mixtures, and these are mixtures in which you can see the individual components. For example, oil and water, when you mix them together, you can see the oil sitting on top of the water. Now, they're not going to be dispersed evenly throughout the entire part of it, they separate, but it's still considered a mixture. Here's a cup. Here's some water. Here's the phase transition. Water is going to be below because water is more dense than oil. All right. And here's the oil sitting on top. Whoop. There we go. And there. So we've got oil and we've got water. That is a heterogeneous mixture. But, as it says here, a mixture in which the composition varies throughout, individual phases of the mixture are easily distinguished. The example I have written in there is a salad. Salad isn't chemical in nature. It's something we eat, so it's probably, I would consider it biological. But you can see the salad, you can see the lettuce, you can see the dressing, the tomatoes, cheese, eggs. You can see the pepper in the dressing if it's ranch. You can see whatever else you put in there, grapes or cranberries. All those things you can easily see, and you can take them and separate them apart very easily. Each of those pieces in the salad that are different are considered phases. Alright, now this is a flow diagram of matter, and it has pure substances, and it has mixtures. And again, we can separate pure substances into elements, we can separate it into compounds. Mixtures can be separated into homogeneous mixtures and heterogeneous mixtures. The example for the element is copper. The example for a compound is water. An example of a homogeneous mixture, aka a solution, is brass here. Brass is copper and zinc. Solutions are normally considered to be liquids like the Kool-Aid, but they can be solids. I have another example of a solid one, which could be steel, which is going to be mostly iron, but some carbon, maybe nickel, and a bunch of other ones depending on the situation. Like there's surgical steel, and then there's just regular old stainless steel. And they have different components of each, or different percentages of each component. The example here of a heterogeneous solution is water and copper. You can see the copper in the cup there, the water surrounding it, forming a mixture where you can see the different parts.